you have a linear program which we call a primal, which looks like something like this, and duality theory allows us to create a dual linear program. It's also a linear program, and I can say what it looks like. Whatever is the number of equations here, right? But duality theory allows us to create a dual LP such that any solution here is an upper bound here. Do you see a relation between these? It's good that you don't. What is going to happen now is that I'm going to talk about duality theory in a very, very different way in terms of upper bounds and lower bounds. We will come up with these programs. After that, we will see this relation. Okay, objective is clear. If I'm given a maximization problem, it's easy to give a what kind of bound? Lower or upper? For a maximization problem, what is easy? A feasible solution will give a lower bound, right? Because the value of any feasible solution will be less than the optimal, right? Now we want to create an LP so that we can give upper bound also, right? Though for few minutes, forget about lower and upper bounds. Look at this great LP. You know, not a great LP, but starting LP. Okay, LP is clear. What is the value of this LP? Exactly. It turns out that the value is 15 because I can just add these two and get the objective function, right? Sounds great, right? My claim is it's what proof you have given me, it need not be 15. Small technicality. Not related to duality, but there is a small technicality, and since we are talking about linear programs, it might not be 15. What have you assumed?
These two constants are satisfied simultaneously by x and x plus 3.
There has to be a feasible solution. If there is a feasible solution, then the optimal value is 15. Correct? And this technical case will keep emerging, keep troubling us in duality theory. So you'll remember this, right? Feasibility is important. If it is feasible, then definitely it is 15. But there might be a case when this is infeasible. I'm not saying about this particular LP. That's why I knew that someone will say, oh, this is feasible. That was not the point I was trying to make. My point was the proof you have given me needs one more thing. Okay? So you guys are good at solving LP. What is the value of this LP? So now the original trick doesn't work, right? What was the trick? This plus this was equal to this, right? Now if I sum them up, what do I get? So I get 2x1 plus 3x2 plus 2x3. Correct? So my objective function is it is this quantity minus x3. Correct? Right? So now what do I know? Yes, you're trying to solve it, but that is not the point I'm trying to make. My point is, we know that 15 is an upper bound. We have started creating upper bound. Right? So now, can I create more upper bounds? What is the general technique now of creating upper bounds? What did I do to create an upper bound? Because we're not interested just in this LP, right? We want to take a dual for a general LP. So, what was the idea here? So, constant in some negative terms. Or other way, I want to construct a linear form which is entry-wise bigger than the quantity here, right? And how did I construct this linear form? It was added, but do I really need to add only, or can I generalize it more? I can take any linear combination of these two, right? I take any linear combination of it such that I get something which is bigger than this, right? Then I get an upper bound, right? What was the 5? This is probably a bad example because I think this 2 will show that x2 is 5. And then actually 15 is the best value, but yeah. But anyway, so the idea is you take alpha and beta such that 1 times alpha plus 1 times beta is greater than 2, right? 1 times alpha plus 2 times beta is greater than. I want to make sure that that when I take the linear combination, the coefficient of it is higher everywhere. So I compared the coefficient of x1, now I am comparing the coefficient of x2. Alpha plus 2 beta is the coefficient in my linear combination. This should be more than what do I know about alpha and beta? Positive, negative? They could be anything. Right? Yes. Alpha and beta are the constants I am multiplying these equations with. So this is generalizing this strategy of creating an upper bound. I say that I multiply the first equation with something, second equation with something, so that I get a linear form which is higher than the objective function entry-wise. Right? Sounds good? If I multiply by alpha and beta, what is my upper bound? If these conditions happen, then what is the upper bound which I get? Right? Should I keep it as this? Should I minimize it, maximize it? Exactly. I'm creating an upper bound. I want the best possible or the tightest possible upper bound. This is the dual of this program. You got your first dual. And again, the kind of connections you will see are amazing. But one of the things which I want to once again emphasize is it's very easy to see now the way we have considered it is that any solution here will give us an upper bound, right? Or what is surprising is that these values are actually equal. There exists an alpha and beta so that you can always, whatever be your LP, you will always get the tightest possible upper bound. This general, strategy of creating upper bound, you were just thinking, oh, let's try it. This is actually the tightest possible. This is the amazing part of duality. It is not surprising that you are getting upper bounds. The strategy was designed to give upper bounds. But why is it tight? So, this is what we call generally, and I will keep repeating these terms, weak duality, but actually okay. And if you want to feel the intuition, what do you think is the reason of strong duality? Hyperplane separation theorem. Yes. It's basically saying, given a convex region, a point outside, however close that point is, but if it is outside, then you can always find a hyperplane separating it. That hyperplane is your dual solution. And I will, when we do the proof of strong duality, you will exactly see this. It's just in one more dimension than the usual dimension. That's why you don't see it yet. But the idea is, but this is coming from this exact point that if you have given a cone, there is a point outside, it doesn't matter how close it is, you can always find a hyperplane separation. So, you have this cone of primal, you have this upper bound. If this is not tight, there exists another dual solution whose value is better. You can keep doing it till you find the best. That's the idea. Okay, but yeah, we will see many examples of this weak duality versus strong duality framework, right? So now we have learned the technique, let's see how to apply it, right? What was the technique? You take the constraints, multiply them by linear constraints. You take the constraints, multiply them by linear multipliers, and then try to give an upper bound, right? So now if this was the equation, and generally now given the state you are in, nobody will give you a linear program like this, probably me in one of the exams just to irritate you, like simplex method. But otherwise, most of the time, you'll have these big linear programs with variables abstractly, and you still have to write the dual in terms of these variables, right? So what is the dual of this?
Transpose B minimize alpha.
How did you come up with it?
But it would be the linear combination of the rows of this thing, so we multiply by.
Okay, good. So let's do it clearly. There are m equations. Right? So now I'm going to have m dual variables. These are the ones I am multiplying by. Now, when I multiply by them, when I multiply y1 times a1, y2 with a2 and so on, they should become bigger than c. Why bigger than c? If x was less than equal to 0, then we would have come up with a thing which was less than c. We want an upper bound, right? If I want to approximate this, if x is positive, then I will say, oh, it is, and now this is an upper bound. If x1 and x2 were negative, I would say, oh, whatever is the value of this, there is a negative thing added to it. It will always be this 2x1 plus 2x2 will be an upper bound, right? So then what you get is I should write it in this way. How do I write it? Yeah, this is a vector multiplication, right? So this is a column vector, everything is multiplied by y, right? Summation over I. So this is a column vector with m entries, right? Did I do it correctly? Yes, yes. And this has to be greater than. So you want it slowly? Look at this matrix. This entire row is multiplied by y1, y2, yn, right? So what do I want? I am looking at, and this is the coefficient of x1. So I want to make sure that y1 times this first entry, y2 times this second entry, ym times this second, third entry, ym times the mth entry is more than c1. Then y1 times the second entry, y2 times the second entry, ym times this is more than c2. I have just taken these row vectors and made them column vector. That's all. Okay. Another way to write it is, now AI is, now y is a vector, column vector with entries y1 to ym. So this is saying Remember matrix multiplication? This gets multiplied by this gets multiplied by this. So y1 is always getting multiplied by the first row. Okay? Cool. So these things are the same. Again, since now, what about the sign of y? It doesn't matter. We could take anything, right? So it's a it's a general linear combination. And what?
Suppose the C transpose greater than equal to C transpose.
No. C, I'm thinking of it as a column vector. Since AIs were the rows, that's why I did a transpose here. But C, I am thinking of it as a column vector. Remember here, it is C transpose. This is a row. So this is X. That's why it is a C transpose. This is a row vector. But yeah, even if it was C transpose, you can do it. So I won't worry about it. Right? This transpose and matching the dimensions, that is something that you can do. Okay? So why? What is the minimization? Sure. B transpose Y, Y transpose B, whatever is your favorite. Okay? So this is the dual of the standard form. Now, there are many things to notice here. In this combination, the most important duality is constraints correspond to variables and variables correspond to constraints. What do I mean by this? By the way we did this, every constraint required a variable in dual. And every constraint that dual arrived from a variable in the primal. Right? And this duality is going to be very important. You're going to see it in many ways. Okay?